so along the Calavicci flow, that the diameter of the exceptional curve goes to 0, so distances in the exceptional curve contract to go to 0. Okay, so we almost finished the proof of number 1, but not quite. What we showed was that if you take any 2 points on a sphere, so we only have to work near D because we know all the metrics are just bounded outside D. It's the neighborhood of the exceptional curve. We see if you're on a sphere, those 2 points, the distance between them is bounded. And we also see that on radial lines, the distance is not just bounded, but actually goes to 0 as the x goes to 0. So for one, so certainly what we can see is that any 2 points, P and Q, which are in D, but away from the exceptional curve, are at a bounded distance. At a bounded distance from each other, because you can just combine these two results. You can like do some radial direction plus some spherical direction, and you're done. So but we do need to check. Well, what happens if you take points that are actually on the exceptional curve? But this is also okay. So if you took but you take P, which is on E, and then take some other point Q, which is in D tilde away from E, then what you can do is, so if I work on D, which is in the image, so 0 sort of represents the exceptional curve, but the different points in the exceptional curve correspond to different tangent vectors at the origin. So it's how you approach 0. So that point P would actually correspond to going into the exceptional curve at a certain direction. So this direction, the direction is P, is represented by P. And then if you take some other point Q out here, well, you can always just, let's do it. Go the same distance out, and then you go around. You see the distance between them is, so this is like P. The distance between them is bounded. So we still get the distance between them is bounded. Okay, so that proves number 1. So now I want to prove number 2. So for number 2, we need to use some additional information, and that is we're going to use the fact that if you integrate E and you integrate omega of t, so E is this exceptional curve. It's a one-dimensional object. You can integrate a 1-1 form, the metric. That's just the volume of E along the Calavicci flow. But what is this? This is the same as the integral of omega naught minus t times c1 of m. This is really a cohomology class, but you know what I mean. And then you can compute this, and this is this is exactly it should exactly be t minus t. Am I getting this right? Okay, sorry. Omega hat t is 1 over capital T, t minus t of omega naught, plus the pullback, plus t times the pullback of omega n. So let me write it like that. So this is the same as this guy, 1 over t minus t omega naught, plus t, the pullback of omega n. But when you pull back omega n, it's degenerate along E, so this actually is 0 when you integrate it. And so you end up with this. So this is just some fixed constant times t minus t. So we're going to use this fact in order to prove that the diameter is going to 0. Okay, so let me explain how we do that. I don't think I need this. Okay, so we want to prove number 2, and here's the idea. So recall that E is just is biholomorphic to P1. It's a smooth rational curve. Imagine you take, let me draw it as a sphere. Imagine you take 2 points P and Q, which are in E. Let's take P and Q, which are in E. And we can always, I want to bound the distance between them, but I can always assume that they're in the same neighborhood, because I can always just take a sequence of points. So let's assume that I can put them in the same coordinate chart. I can put in the same coordinate chart, but they're not too far away from each other. And let's assume furthermore that we have our coordinates. So let's identify this with a coordinate chart like this. And let's assume that I can always choose my coordinates so that P is the origin. And Q is the point, say, x0, 0. And let's assume that on this chart, the Euclidean metric is uniformly equivalent to some fixed metric, say omega naught restricted to E. So I assume that we're working on a coordinate chart, and I can just assume the Euclidean metric is just some fixed metric. So we fix our coordinate chart. Okay, there's a trick. What we're going to do is we're going to use this integral bound. So I'm going to use the integral bound to get a distance bound. And in the process, we're going to lose a little bit. But the idea is very simple. What I want to do is take a rectangle around these points. This is the point P. This is the point Q. Let's take that to be epsilon. Okay, so we consider let's call this rectangle R. So we have a rectangle R, which is just, let's call this point x0, say, x0, x0, 0. It's just 0 x0 cross minus epsilon, epsilon. And then if we integrate over R, if we integrate omega of t, then this is bounded by a constant times t minus t. Okay, that because it's just some subset of the whole of E. It's just less than the integral over the whole of E. Now, okay, I want to choose a particular epsilon. I want to choose epsilon to be t minus t to the 1/3 power. And now, this is just use Fubini's theorem. This is the same as the integral from minus epsilon to epsilon and the integral from 0 to x0 of, say, g of t and then x, y, and then dx, dy. Okay, so this is this. So remember that a Calavicci metric is locally given by an n by n Hermitian matrix, but here we're on a on a Riemann surface. We're working on E itself, and so that Hermitian metric is just 1 by 1 matrix. So it's just a real number. So I can just think of the metric once you fix a coordinate chart. It's just a real positive number. So I can integrate it, and that's bounded by this. But on the other hand, if this integral is less than this, then that implies that for some number between minus epsilon and epsilon, let's call it y prime, between minus epsilon and epsilon, I must have that the integral from 0 to x0 of g of t x y prime dx, this had better be less than a constant times t minus t divided by epsilon. Because if that were not the case, then all of these would be bigger than this, and then when you integrate from minus epsilon, epsilon, you would contradict this inequality. So at least one of those lines has to be bounded by this. But now I choose the epsilon to be this, so this is nothing other than, this is nothing other than a constant times t minus t to the 2/3. Okay. And now we're almost ready to finish. And you see, this is very non-optimal, this kind of argument, but it works for what we want to do. So now what it means is, if you take look again at the rectangle. Let's suppose this point is my y prime. Then let's call this point here, let's call it p prime, and let's call this point here, say q prime, and let's look at the distance from p prime to q prime. Well, by this, okay, so the distance from p prime to q prime in the metric g of t has to be less than the length. So it's less than the integral from 0 to x naught, and then the square root of g of t, and then I'm going in the x direction, so I get ddx, and then dx. Where I'm evaluating, where I'm evaluating at x, y prime, dx. Okay. But now you just apply Cauchy, the Holder inequality, and this is bounded by the integral from 0 to x naught, some constant times this thing squared, to the 1/2 g of t y prime dx to the 1/2, just by applying the Holder inequality, just square that. L1 norm is bounded by the L2 norm, and then this we said is bounded by this, and so this is bounded by a constant times t minus t to the 1/3. So we wanted to bound the distance from p to q, but we ended up bounding the distance from p prime to q prime. But on the other hand, notice that, of course, the p prime is very close to p, and q prime is very close to q. They're within an epsilon of each other. And now I claim that it's not difficult to do. So this is p prime to q prime, sorry. But then the distance from p to q is going to be just this distance and this distance. This is epsilon in the Euclidean metric, but I claim it's also bounded by a constant times epsilon in the g of t metric. So let me just explain that in a second. Write down this distance, and then this then is just, since epsilon is t minus t to the 1/3, I just get this. So why is that? Well, if you get 2 points which are very close to each other in the P1, it means that when you look at these correspond to different directions going into the origin, but those directions are extremely close to each other. And yet we've said that if they're extremely close to each other, then because of this bound we have on g of t, the distance, like the angle is like an epsilon, and then you just got to bound this again by an epsilon. So that's enough to get this bound. So we get that this is bounded by a constant t minus t to the 1/3. Okay, so this bounds this. Okay, so this is Yeah, but this is just all. It's just bounded. I'm working on some fixed coordinate patch. So the L, when you're working on a compact set, I mean the L1 norm is bounded by a constant times the L2 norm. Yeah, I fix my. I fix my. I assume that P and Q are relatively close to each other, because if not, I can just find a sequence of points and I just fix some coordinate chart. That's fine. Okay. So now, okay. So this is actually the where I'm going to sort of move on. So I'm not going to really prove any. I'm not going to prove anything else, in some sense. I want to just mention. So what can we actually prove? So furthermore, what we can show is that so we have this metric omega t outside of E. Then in fact you can identify the completion of M minus E with this limiting metric omega t. So this is the metric completion with n d, what I call dt, where dt is just a metric. So where dt, you simply you define this metric. It's a metric in the sense of metric spaces on n, and it's given by just simply taking omega t away from y, this point which is which you've blown up, and just replacing omega t by the zero metrics at that point, and that gives you a distance function. So you're just completing by just adding a point. So what you do is you just take it to be this on n minus y, and just take 0 on y, and then you could define distance in the usual sense, and then it's a theorem. One has to work quite hard to prove that the metric completion of this is exactly this metric. And then moreover, you can use results of Song and Tian to say that you can start the flow from omega t, and it immediately becomes smooth. And moreover, what we can show is you get Gromov-Hausdorff convergence of m of omega t. This will converge as metric spaces to n dt. And then if you consider the n of omega t for t bigger than t, so these will be the flow starting from this singular metric omega t, this will converge backwards in the Gromov-Hausdorff sense, so as convergence as metric spaces. So it turns out that you get this contracting of the -1 curve in this sense of Gromov-Hausdorff, that the metrics will converge to this n dt, which is a metric completion, both forwards in time and backwards in time. And that's what we call kind of metric contraction of the -1 curve. Okay, so in the last half an hour or so, I want to instead talk about some open problems in new directions. Okay. So I want to talk about some open problems and new directions. So as I said, that with Kähler surfaces. Yeah. No, that we don't know. Yeah, I don't think so. I don't think it would be true, but I guess it's plausible it could be associated with a smooth 1-1 form, but I don't think it would correspond to a smooth metric. But I can't prove it either way. Okay. So as I said, with Kähler surfaces, we have generally we have a very good picture of what goes on. But there are some questions that remain, and the questions that remain probably are quite difficult. But one of them is that, so in this particular case, so as t tends to this capital T, there's a question about what happens to the curvature. We never talked about curvature here. We didn't really need to. You might ask, do we get what's called a type 1 singularity? So do we have... It's conjectured that we do. Generally conjectured that all finite time singularities for the Calavicci flow should be type 1. So we might ask this question. That's the so-called type 1 singularity. Another question, harder than this, is suppose this is true, then can we do a blow up? So this can we do this rescaling? So suppose you have Tj tending towards capital T, and you have that the Riemann curvature at some points, say xj, Tj is equal to kj, which goes to infinity. You can do this rescaling procedure, so you define Gj of T to be kj G of, I'm always going to get this wrong, Tj plus kj minus 1 of T. So T is in some appropriate range. So you get some flow of, you get a family of flows, and then satisfying the Ricci flow. And then the question is, what do they converge to? So the conjecture is that these converge to some G of T, so converge in the sense of Chigov, Gromov, Hamilton. Well, I guess you would take this pointed convergence where you take the points xj, converge to GT, which is a Calavicci soliton on the blow up of C2 at the origin, and there's a specific soliton which was constructed by Feldman, Ullmann, and Knopf. So this is really getting the higher order information about the singularity. So we know what we know some things about the singularity, but we really want to know, well, when you zoom into the singularity, really what's happening. And this is a well-known conjecture. And this is shown, actually, both of these have been shown by, so this is true for some U2 invariant metrics. Invariant metrics. In the case of P2 blown up at one point, and in higher dimensions, the higher dimensional analog. And this was shown by work of Maximo, who did some cases, Janson, and Binguo and Janson. So under some assumption of symmetry, large symmetry group, that this is known to be true. It's surely true in general, but it's still an hard open problem. Okay. Another interesting question is number 3. Or maybe I'll make a bit more space. Another question is about is finite time collapsing? So it's a very simple question to ask, but it seems to be very hard to answer it. Let me give an example. So again, let's go back to this manifold. The blow-up of a point on P2. So this is Kähler surface. And there are three behaviors. There's three possible behaviors of the Calavicci flow. And the behavior depends on the choice of the initial Kähler class. It only depends on the class. One is that if omega naught is in the multiple of the first Chern class, here lambda would be a positive constant, then you get that the manifold shrinks to a point. In the Gromov, the diameter just goes to 0, and that's due to Perelman. Follows some Perelman's estimates. If you rescale, so it makes sense then to rescale a flow so it has fixed volume, you get a Calavicci soliton on P2 blown up at one point. And that's it. So this uses ideas of Perelman. The proof is, I guess the proof would use the existence of the soliton. I'm not sure who that's due to actually. Maybe Koizo. And this is or White and Tsao, I'm not sure. This is but the convergence is due to, was written up by Tian and Zhu, which uses some ideas of Perelman. Okay. So another possibility. So as I mentioned before, that of course CP2 blown up at one point, of course, has an exceptional curve. So another possibility is the exceptional curve goes to 0 in finite time, and so what you have is the contracting. You contract the exceptional curve, and this is exactly the situation that we've been looking at, and so you can apply our results, these results that I have with Jan Song. But then there's a third possibility, because the CP2 blown up at one point also has the structure of a bundle over P1. So just as in the case of, so if you remember, in the case of you blow up, eventually you blow up 0, C2, you always have a map to P1. It's the same thing with this. So you have a map to P1. This is actually a Ruled surface, and then what happens is that so you can think of this as a P1 bundle over P1, and then what happens is that the fibers of the P1 bundle collapse as T goes to capital T. So this is an example of a manifold where the Cadao dimension is negative infinity, and you see that you get different behaviors depending on the class. So it's a little bit more complicated than the case of Cadao dimension bigger than or equal to 0. So this is the case which is really not understood. Okay, so this is not fully understood. So I have some partial results with Jan Song and Gabor Zekahidi. We showed, for example, that using a very similar argument to the one I just described, is that you get that the diameter of the fiber is bounded by a constant times t minus t to the 1/3. Again, of course, t is finite here. So we get this bound which is t minus t to the 1/3, but this is not optimal. It should be 1/2. And this argument is very non-optimal. It's the same argument. So we get that, but yeah, we can't do better. And what you'd like to say is that you get some convergence to some smooth metric, I guess, on the P1 base. It's not known. And you could even take a much simpler example if you want. You don't have to take a bundle, you can just take a product of a Riemann surface cross a P1, and it's not known what the metric behavior is. So it's a very simple problem to state, but it seems to be very hard. At heart, the difficulty is that these fibers are P1s, and so even the Ricci flow on P1 is a very hard problem due to Hamilton and Ben Chow. I don't know any simple proof that the Ricci flow converges on a P1. And here what you have is like a family of P1s. So you kind of need a kind of family of a family version of the Hamilton-Chow result. Seems pretty hard. Okay. Let me mention. Oh, okay. Yeah. Then of course number 4 is of course a higher dimensional. Is the higher dimensional birational transformations. So we talked about the curves shrinking to a point, but if you're talking about complex dimension 3, then you can have much more complicated behavior. You can have something called you may have something called a flip. So you may start with a manifold of Cadaro dimension bigger than 0, and if you have a singularity in finite time, it means you have you're going to have some of the canonical bundle's not left. Anyway, let me not get into the details. You have some curves there, and what can happen is you can get something called a small contraction. And this is what happens is that some curves shrink to 0, and you map to a manifold M tilde. So along the small contraction, you get some curves C satisfying that K dot C is negative, and those curves should shrink to 0 along the Calavicci flow. But then there's a difficulty, and the difficulty is that this is actually singular. A singular variety, and somehow too singular to work with. And the result, the way the one deals with this in algebraic geometry in the minimal model program is that you construct a new manifold, maybe it's called M plus or something, which also contracts. It contracts but this one actually contracts curves with K dot C positive, and then this map is birational map, so it's an isomorphism away from some subvariety of codimension 2, and then the idea should be, so this is the program of Song and Tian and the big minimal model program. The idea should be that the Calavicci flow should somehow maybe even construct for you this is called the flip. You should construct for you this manifold, and you should get a solution of the Calavicci flow on this new manifold here. And these two are related by this singular guy here. So anyway, so this is very, very far from understood. There's some examples worked out by Jan Song and his collaborators, but even then it's really very far from completely satisfactory. Okay, so those are some very well-known problems in Calavicci flow, which means that they're probably very hard. Let me mention a couple of just two new directions where I think that.
So in this picture, right? So this is more like an algebraic geometry picture, right?
This is like algebraic geometry, yeah.
So in Calavicci flow, so what do you expect,
Well, here you'll have a family of metrics.
So you hope that you would.
You would hope to construct a family of metrics here as well. And I guess that as t goes to some finite time capital T, this will converge to some metric space. And then this, as t goes T from backwards, it should be some other metric space, and they should coincide. Yeah, that's the picture. So you can do all these things. these kind of things you can do on the level of potential. So Song and Tian worked a lot of this out. But knowing what's happening at the level of metrics is very hard. It's not known. Okay. So I wanted to point out a couple of new directions where, newer things that people are thinking about, where I think there's still a lot of maybe low-hanging fruit, so to say. And one of them is the conical Calavicci flow. So what is this? If you're given a manifold M together with a hypersurface, it's called D. You can think of it as a curve if M is two-dimensional, or you can even take M to be one-dimensional and D would just be a bunch of points. Then you can define a conical metric along D with cone angle beta. Let's call this omega. So omega should be smooth outside. It should be smooth on M minus D, but it has some prescribed singularity along D. So along D, I want to think that I have like a whole bunch of cone points, like a line of cones. It's a variety of cones. So near D, so on D, let's suppose D is given by Z1 is 0 locally. Then omega should look like root minus 1 dz1 wedge dz1 bar over Z to the 2 1 minus beta plus some plus just the Euclidean metric and the other factors. Okay, I think I got that right. So this is called a conical metric along D, and these guys have been studied a lot.
D is codimension 1.
Yes, D is codimension 1. So these have been studied a lot in Kähler geometry because they have they were a crucial ingredient in the proof of the Chen-Yao-Donaldson conjecture. So what you see is that, okay, so then the question is you look at this so-called conical Calavicci flow so at the level of currents, so as currents, so it's 1-1 current, so I allow these 1-1 forms to have, sort of just coefficients which are just measures, and then you get something like 2 pi times 1 minus beta, and then D, this is let's say this right as TD, I think that's what I was doing, this is the current of integration. Integration along D. So the idea is where you start off with omega 0 is omega which is conical. And the idea is that this coincides with the Calavicci flow outside D. So this is the Calavicci flow on M minus D. And the idea is that it doesn't smooth away the conical metric. You actually keep the conical metric. So the idea is that you keep the conical singularities along the flow. And so people have worked on this, and for example, in the case of Riemann surfaces, there's work of Matteo Rubinstein, Natasha Sezin. There's work of Fong, Song, Sturm, and Wang. There's work of Chen, Shen, and Edwards, a student at Northwestern. So there's many works on this. So in many cases, if you make an assumption about the initial metrics that's not too sort of easy to understand, you can say a lot of things, and you can reprove a lot of results from Calavicci flow. But even the basic short-time, as far as I know, the basic short-time existence result, which would say, given a conical metric, the flow remains conical, is not yet proved.
So in the flow, is the angle fixed or
the angle is fixed. The angle is not changing.
Is fixed. It's not going
Yeah, it's not going to change. It should maintain this form. Exactly, it should maintain this form along the flow. But as I said, it's at the point where it's still very early, and no one really knows quite what the. I would say people don't exactly know what the right formulation is. Why is it interesting? Well, it turns out that this minimal model program, if you, so this, all this is the minimal model program. From the point of view of the algebraic geometers, they don't work with varieties. They work with what are called log pairs. I don't know anything about this really, but they don't work with a manifold or a variety. They work with a variety plus an R divisor. And so really the right way, I would guess, the right way to think about the analytic minimal model program ought to be with these pairs. And you probably need some kind of notion of conical metric or metrics with singularities along D. Seems to be the appropriate thing. But again, no one has really worked it out what the connection is. And okay, the last couple of minutes. So number 6 is what happens if M is not Kähler. So this is something actually I've been working on for quite a bit of time. So let's suppose you have this M is two-dimensional. So this is M is a complex surface. Well, you could of course ask what happens to the Ricci flow, but the Ricci flow doesn't preserve the complex structure in the sense that if you have a metric which is Hermitian, which is J invariant, the Ricci curvature is not going to be J invariant in general, and so you're going to immediately go from being a Hermitian metric to being non-Hermitian. So the Ricci flow kind of kills that invariance of the complex structure. So the Ricci flow is not somehow the right flow for this category. If you want to stay in this category, it doesn't seem to be right. So instead one looks for a flow, you want to look for a flow of Hermitian metrics. And there are many different candidates. You can write down, such flows and infinitely many such flows. But the one I've been looking at is called the Cherokee Flow. And it's very simple. It just has basically the same formula as the Calavicci flow. Namely, you take this. You take, this is just the formula for the Ricci curvature of a Kähler metric. You just take that as being your definition of your flow. And this is called, this guy here sorry, it should be a plus. This guy, so this will coincide with the Calavicci flow, because minus this is the Ricci curvature, so dt of m minus the Ricci. But this is called the Chern, but in the case where G is not Kähler, this is called the Chern-Ricci flow. It was first introduced by Matt Gill, who was my student at San Diego. And so this or minus this is called the Chern-Ricci curvature, and the point is that it's the Ricci curvature of a certain connection, but it's not the Ricci curvature of the Levi-Civita connection. So what you lose is a bit of that connection with Riemannian geometry. But on the other hand, it turns out that for Kähler surfaces, so for complex surfaces, most of the same picture that we saw for Calavicci flow goes through. So almost everything. you start with a complex surface, non-Kähler, with Cadaro dimension not equal to minus infinity. And then what happens is the flow will exist until some minus 1 curve shrinks to 0. What we can show is you get smooth convergence away from that minus 1 curve. So this is work with Valentino Tossati. You get convergence to the metric outside that minus 1 curve. What we'd like to show is those minus 1 curves contract to 0, and you can continue in the same way as the Calavicci flow. We can do that under some additional hypotheses, but we don't know how to prove it in general. And then you keep doing it until you get to the minimal model. And on the minimal model, in Cadaro dimension 2, you get convergence to a Kähler-Einstein metric. So that actually becomes Kähler in the end. In Cadaro dimension 1, you will get, so with Tossati and Shakwa Yang, we showed that if you started with if you had something which was non-Kähler, it actually is an elliptic bundle over a Riemann surface, and you get contraction of the fibers, and you get conversions to some twisted Kähler-Einstein metric on the base, and then in the case where you could out dimension 0, you get conversions to a Cherokee flat metric. That's due to Gill. So the basic whole picture from the Calavicci flow, with some, there's some still ingredients missing, but the basic picture looks like it's there. It does seem to follow that same kind of pattern. So these are fairly recent things. Just in the last few years, these have been studied. So I think there's lots of interesting problems for people to work on. Okay, and maybe I'll stop there.
For this problem, right? You start from any Kähler surface, and it's also the same category of behavior like this.
This particular example has Cadaro dimension negative infinity, so that's why you can get these different behaviors, like shrinking and collapsing. In Cadaro dimension bigger than equal to 0, you don't. The only one you get is this middle one. It depends on the Cadaro dimension. But in Cadaro dimension negative infinity, yes, you'll get one of these three behaviors in finite time.
And for the initial, it's not in the class. Any initial condition, can you have some idea?
What do you mean?
Depend on the initial.
Right. It all. You can write down what exactly the, it depends on the intersection numbers with this and the exceptional curve or the fiber in here. So you can write down. It's just a numerical thing. You can just write down what the conditions are on omega naught, and it'll tell you which one of these you're in. You can read it off from the topology. In general, in Cadaro dimension negative infinity, you can do the same thing.
So for the conical scenario, right? So won't there be any restriction on how the conical angle?
The angle certainly comes into it. Yeah.
But there should be some restriction. Right?
This is the angle. Yeah.
No, but is there any restriction on how large or how small of the?
The angle is between 0 and 1. I should have said.
So it can be free. So if there's no certain number will not exist or.
No, it doesn't seem.
Because I know in the case of a Riemann surface, right? Say if you have some puncture point, right?
Oh, it'll change the behavior of the flow, sure.
And then I think there's some restriction on the total cone angle, right?
Yes. Yeah, that's right. Yeah, so you'll get like this sort of. So here, here, for example, the behavior of the flow will depend on the initial metric and the cohomology class of that, but in this case, it will depend on the cone angle too. Yeah. So it'll be some cohomological condition involving the cone angle, the divisor, and the initial Kähler class. Yeah, exactly right. Yeah.
Is there any reason why you need to be smooth over there? Could you have like a normal crossing?
Yeah, I think you should be able to, it should also make sense for normal crossing. And actually Greg was working on this, and Greg Edwards, and he showed that in certain cases, I think you expect to get the devices. It doesn't have normal crossing, so it could even have, perhaps one has to work out even more complicated things. Yeah. Well, it's not been worked out, but I think you have to deal with those cases.
The best is train for very clear and also interesting problem. So let's thinking for working very hard for 6 hours. Let's think so for the all the lectures.